What's up, guys? So we are back again in a new spot once again.
This time in a bunker.
Right.
This time in a legitimate bunker.
Right. So hopefully the lighting's all good for you guys.
Yeah.
Just to start out, make sure you like, share, comment, subscribe to the channel if you haven't already. And make sure you check out the website, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then, once again, thank you, patrons. We greatly appreciate the support, guys. We couldn't do it without you here, helping donate to the show. And if you are interested in checking us out and becoming a patron yourself, just go to patreon.com/Eigenbros, and me and Juan do a 30-minute audio podcast there every week. And we've also got the official Discord up there now, too. So if you guys want to just have conversations and give us, podcast guest recommendations and whatnot, go check it out. So, and I think that's all we got to do with the beginning stuff. Mm-hmm. Let's get to the topic.
Yeah, the topic at hand, quantum information.
Indeed.
The beast.
One I've been avoiding for a long time.
Yeah, well, we've been avoiding for a long time because, not for nothing, it's a modern topic.
Yeah, which always means that you're going to have to piece together a lot of the information yourself to get anything really valuable.
Yeah, so like as most of you fans know, we kind of pull from various resources because it's a long format show.
Yeah.
We use a lot of resources that are out there. We kind of serve as a guiding hand.
Sure.
For some of these topics for a lot of you.
Right.
Something
that you can take away, hopefully, that's going to, elucidate something new. At least.
Like if you're like, because I think there are some misconceptions about what we do here at the podcast.
Is there?
I think so. There was a comment I read. Somebody was like, "Yeah, you guys just look stuff up that I can look up."
Really? I didn't even see that.
And I was in my head. I was like, well, yeah. I mean, anybody could look anything up.
Well, I try to make it so that we give at least some, something new.
No, same here. Like I want the listeners to walk away with some kind of like, okay, that either I walked away asking more questions. Because think about it, the whole point of a question, part of it is like you're going on a quest. That's part. You can't spell question without quest. You know what I'm saying?
Deep.
That's something to think about. But you really, it's to kind of motivate you to seek answers.
Yeah. Yeah.
And I mean, a lot of this is kind of an introductory thing, but me and Terrence are interested in like turning a lot of the big concepts like quantum field theory into a whole series, and then the same with quantum information. There's just so much to cover.
Right.
And these concepts are so intricate that they might be better served as like a whole series. Right?
Maybe. Yeah. We'll see. Time will tell.
Time definitely will tell.
I don't like to overpromise, but
we'll see. For sure. Like I said again, a hope, maybe a distant one, but still a hope. But I did kind of want to consolidate some things that we kind of figured out. Quantum information, just getting right into it, is, like I said, like we were saying, a modern theory, but it has its roots in like kind of something that we're familiar here with, like as physicists. It's the EPR paradox.
Mm-hmm.
Einstein, how do you pronounce his name?
Podolsky and Rosen.
Mm-hmm. Very famous for also their. That's kind of like a super team if you think about it.
Right.
Like
all those guys are like super team back then. It was crazy the level of, smart people back in those days with the whole, Solway picture. You're just like, God damn, they all existed at the same time.
Yeah. If you're a sports fan, this is kind of like the basketball equivalent of the dream team.
Pretty much.
You know what I mean?
Right.
It's like everybody.
The MJ era, right?
Yeah. It's like Einstein is obviously the MJ, Michael Jordan.
Yeah.
And world famous in a similar way. He really put physics on the map for a lot of people. And in a lot of ways,
he also had like Dirac.
That's true.
And like Heisenberg and Bohr and like
von Neumann.
Yeah,
I think he was there too.
Right. It's like
Curie was there too.
Yep, Curie. It's like God damn.
All the big names in modern science. Insane.
Yeah.
Like you don't have that relevancy today because I guess like. And maybe this is another question for another time, but
yeah,
like it kind of digs deeper into like why don't we? What's up with our scientists today? Like, why don't we have these kind of like?
Well, I think also today is a little bit different because theoretical physics is so hard right now that we're like pushed up against the wall. And then the only like real innovative stuff right now that's happening is like real like super bleeding edge experimental physics is like these really giant, experiments like the LHC, like accelerators and whatnot.
Yeah.
So it's like things have just gotten so hard. I think, but the nice thing is I think physics is becoming more communal or something, you should say.
Yeah.
Where it's like a lot more physicists are coming, and it's less like the lone wolf now, which I think is better, honestly.
Me too. Yeah. My take on this is that I think it's just because we haven't had another subject like quantum mechanics kind of rear its head. Well, I mean, I guess like in this kind of burgeoning way, like quantum mechanics is like foundational stuff. I don't think we've had a field like that in a very kind of
like a new branch of physics.
Yeah. Right.
I'd say maybe computational in some sense.
Okay.
Because computers are so like, I mean,
modern.
It's like it's related
to
the topic, right?
Yeah.
So it's like computers are so promising and have so much what would you say, potential with doing physics. It's like that's a real big frontier, I think, because we can do so many new computational tools now. And then like we're talking about today, quantum computing. I mean, the problems that we will be able to solve potentially, I think, are really numerous, and I don't think we even have any idea how big it's going to be when it actually hits.
Yeah, no, for sure. And this is kind of why Einstein is the Michael Jordan of physics, because
why is that?
Einstein is kind of the person that like literally got the ball rolling on a lot of different things, and quantum information being one of them.
Really?
Because he was debating in the EPR paper. He was debating about entanglement. He didn't trust it. He had this fundamental what I think one of the physicists was saying. They said Einstein had a philosophical prejudice.
Yeah, I mean it makes sense, right? Because it defies intuition, and Einstein is the god of intuition, right?
Yeah. And for those of you that aren't in the know, Einstein and Bohr had a dispute about the interpretation of quantum states, especially like entanglement or entangled states, which have this non-local, what people would say, statistical correlations. You know what I'm saying? Like entanglement, essentially.
Spooky action at a distance is what they call it.
Exactly. That's kind of the colloquial way that you put it. But in more technical terms, it's non-local statistical correlations for space-like separated systems. And like what I mean by space-like is essentially light you can't send a signal there faster than the speed of light. Yeah. Essentially.
So particle A and particle B exist in the universe. Particle A can only interact in its local region, which would be just a radius the size of the speed of light.
Yeah.
Of course, it can propagate, but it's going to take time to get to particle B before it influences it.
Exactly, yeah.
So things that can influence if particle A can influence particle B in some kind of way that's outside of that region, that's the size of the speed of light, or the length of the speed of light distance, you could say, a light whatever distance, then that would be non-local.
Yeah.
If it can influence it outside of that radius.
Yeah, for sure. And Einstein did not like this entanglement stuff. He didn't like the spooky action stuff.
Right. With good reason, for sure.
Sure, yeah. And I mean, this kind of thought experiment kind of drove other physicists to reply, because like a lot of this was swept under the rug in a lot of ways, and people didn't want to deal with the philosophical implications, let alone philosophical implications, but also the physical implications.
Yeah.
Einstein took the position that quantum mechanics is incomplete. It's we there's something we don't know that's giving us this stuff, and yeah. So this discomfort led I think Schrodinger, funny enough, to reply. And I didn't know this, but Schrodinger was actually the person that coined the term entanglement.
Oh, I didn't know that either.
Yeah. Especially the way we used it today. He the way he put it was just I think I have a quote here. He said, entanglement, he wrote a whole paragraph, and I'll put it up for the listeners here. He said, in 1935, when two systems of which we know the states by their respective representatives enter into temporary physical interaction due to known forces between them. By the way, run-on sentence is like a mother. And when after a time of mutual influence, the systems separate again, still a run-on sentence, then they can no longer be described in the same way as before, vis-a-vis by endowing each of them with a representative of its own. That's a whole sentence. That guy just made a whole sentence there.
Physicists are not the best writers all the time. We'll just say that.
He said, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought, the interaction of the two representatives, the quantum states, where they have become entangled. Yeah.
Okay.
Yeah, a little verbose and a little bit kind of messy. But he says all that to kind of say that that entanglement is the characteristic trait of quantum theory that enforces its departure from classical physics. And this is something that, at least for me coming into grad school, I think was an enlightening thing. Because I think my professor also was like, one of our professors, I think, said, what makes the fundamental feature of quantum mechanics deviate from that? And he said entanglement. Do you remember this?
No, but that was definitely something that was answered for me in graduate school. I don't remember when, but yeah.
Yeah, and that's something that I didn't really internalize up until, we got to the part about Bell. And this is something we did last episode about delayed choice, but Bell's...
Well, 3 episodes ago.
3 episodes ago, yeah. So John Bell did an analysis kind of testing this EPR paper, or replying to this EPR paper. If you think about it, this was almost 30 years after that EPR paper came out. Like, he replied in 1964.
Wow.
A rebuttal.
Yeah.
Yeah. And this kind of blew, like, the lid on
hidden variables and all these other, like, weird... trying to make it classical, or trying to put these classical interpretations on quantum mechanics. Yeah, that's when you really realize that, quantum mechanics truly is its own, like... Yeah. It truly is. This is the fundamental state.
Yeah. Like separability and locality, these physical concepts in our realm that seem like reality.
Yeah.
Bell's inequality test showed if you put two parameters... what it would say, two quantum mechanical parameters together and tried to test them, they're incompatible with certain quantum statistical correlations. So, yeah.
Care to unpack that?
No, I don't. That's going to be its own video, but we actually did a video on this already, so you can go look at that.
On Bell's
inequality.
Yeah, we did. An old one. I don't know if it's good, though, so...
Yeah, another qualifier, a disclaimer.
Yeah.
Yeah, I'm not sure. That was a long time ago.
Yeah, so long ago. I don't remember anymore.
If you want to, go look at that, because that really does require its own episode. But but the idea of like separability, that's the word that I'm looking for. Separability, yes.
Yeah.
Because we often see ourselves integrated into. We in science, I guess, we don't see ourselves integrated into the experiment.
Right.
You know what I'm saying?
Right. Or with quantum mechanics, it's kind of a fundamental part of the theory. It's like it's finally building in the people and the apparatus that measure these things into the system.
Yeah.
Now they're inextricably linked in some fashion.
Yeah. Like we have this like sort of detached observer kind of perspective
with classical systems, for sure.
But all these concepts got kind of flipped in their head after Bell introduced this sort of stress test of locality and causality. Like these things didn't really apply in quantum systems, and that kind of like shook the physics world.
Yeah.
But this in particular, in the Bell test, they do stress entanglement. Like entanglement is a huge part of this this feature, and building off of that, there were later experiments in the 80s confirming the sort of non-classical correlations, and excluded any sort of like physically plausible non faster than the speed of light
Yeah.
classical communication between these like separated setups.
Mm-hmm.
But yeah, anyway, it wasn't until later that you get like other physicists kind of thinking more about the applications. Like they were like thinking like, okay, how can we exploit these features of like the measurement process to kind of like have some kind of communication between people, right?
Yeah.
And this is where like we get the kind of like the first test of like cryptography, like quantum cryptography a little bit.
Oh, would you consider that
Yeah,
sophisticated enough to call it that?
Well, because like two scientists were trying to figure out ways to communicate to each other.
Okay.
And they started trying to put thought experiments together
Mm-hmm.
and saying like, well, if I give you a particle.
Yeah.
Sorry, let's say we have two photons that are entangled, and you have one and I have one, right? They start thinking about, well, like, how can I transfer information to you that isn't like going to break the laws that we know, and like what kind of features would we have if we're able to communicate information to one another?
Mm-hmm.
And so they came to, I think famously, you have that like quantum cryptography idea. You know what I'm talking about? How you can stop eavesdropping.
Right. Well, this
is
is called the I think it's called the Superdense protocol or quantum protocol. I forget exactly what it is. MichaelNielsen actually has a really good video series on it called like quantum computing or something, or quantum computing for the determined.
For the determined?
Yeah, for the determined. It's actually really nice and well done. I'm a big fan of MichaelNielsen's work. He always makes things very easy and explainable.
Yeah.
We've used his stuff for the Yang Mills video. So yeah, I would definitely recommend checking out that series.
Yeah. Yeah. They do.
That's even the video I sent to you for this podcast potentially if we get any time to do it.
Gotcha. Well, maybe we will. I don't know, because this opened the door for like how you can have key distribution. You know, where you have two parties, like say me and Terrence. We share no information.
Who's Alice and who's Bob?
Alice and Bob, the classic.
Right.
Who's Alice and Bob?
Yeah.
I'll be Alice. You can be Bob.
Okay.
Mostly because I get to pick first. Alice always gets to go first. So.
True.
But yeah, Alice and Bob, they share no information but end up holding a secret random key which can be used to send encrypted messages between two parties. Now, this is obviously a thing of interest, right, to engineers, but physicists are always at the ground level for a lot of this stuff. So,
right.
Yeah, they started playing around with this, and you kind of get into a weird concept like quantum teleportation.
Right.
What some people call quantum teleportation. But teleportation seems like a funny way to
it's a misnomer for sure. It's like one of these things that's kind of a little bit misleading. Because when you think teleportation, you think Star Trek, right?
Yeah.
You think you're beaming up somewhere, but that's not really what it is.
Yeah, okay, there's this idea of cloning, and I think I brought this up with Terrence, and because there's a no cloning clause in quantum information, and we'll talk about it more later, but quantum teleportation is a very important feature to even have any kind of information shared. Going into this Alice and Bob like thought experiment, Schrodinger posited, because he was the one that kind of played with this idea first. He was like, if you have an entangled state that could be, if there was a way that you could steer an entangled state into a different set of known states. Does that make sense? Like you and I share a particle that's entangled, so we know the available eigenstates. Right?
Yes. Yeah.
And is there a way that we can steer it into
A particular state?
Yeah.
Yeah, and they figured that out with the Superdense coding protocol.
Yeah.
Yeah.
So, but this goes down to, but this has its roots in back in the 1930s.
Oh,
Schrodinger.
wow.
Yeah.
Okay.
Like, and the thought experiment is like as simple as like Alice and Bob, the classic. Like I was saying, they share
Can't fail.
They share two entangled photons, one with Alice and one with Bob.
Mm-hmm.
You know, and like I said, they both know the eigenstates of the entangled pair. For those of you that aren't familiar with what eigenstates are, it's sort of the set of common states available to the entangled pair, right? Would you say?
Yeah. You could just say because qubits are 0 and 1 with the Superdense coding protocol, you have two qubits basically. So you have two. You know, there's the regular bit and then there's a quantum bit. I'm not going to keep going over that too much, but most people are aware, I would say. So then you have the two qubits and they're entangled, and you can send one of those qubit states to Alice, and then you send another qubit state to Bob, and then Alice puts that qubit through some series of, or one of these quantum logic gate transformations, and then she sends the qubit to Bob, and Bob can decode it using his qubits, the two qubits together, and then he can figure out what state was used. So basically, the logic gate that Alice used on her end, on her qubit, will tell you some kind of information when she sends it to Bob.
Yeah. And this is like
hopefully that made sense. MichaelNielsen has a very good, thorough video of that.
That's kind of the modern application of like the thought experiment that Schrodinger had, because like his was like much more rudimentary. It's a much simpler toy model.
Yeah, sure.
Because he was just like, he didn't develop an algorithm or anything. It was just kind of like I was saying, just a thought that he wrote down in response to this EPR paper. But yeah, so with Alice, so the way that he was thinking is like, however, if Alice introduces a photon in her system, that she doesn't know, like she doesn't know what the states are accessible to it, so. Meaning she doesn't know the basis states of the quantity they're trying to measure. Right? And let's just say Alice decides to measure the system.
Okay.
Now, so technically the Hamiltonian of this particle that Alice has now includes the entangled photons, because I'm sharing with Bob, right? Plus this unknown state of the particle that she introduced, right?
I lost you a little bit.
Okay, so we had Alice and Bob. They shared a entangled pair.
Yep.
So you have that Hamiltonian of the system just has the two particles.
Sure.
Right? The two particle states. But now she introduces a third state in her system.
That's not what I am aware of seeing.
But this is
There's no
Schrodinger's
third state. It's just she does an operation on one
that's
of the
qubits. This is the modern.
So
one.
it's not change. It's not adding a state.
No, like she's introducing another particle. In this
so
example,
you're gonna have to take that one away because I don't know anything about that.
In this example, she decides. So she introduces another photon in her system, but remember, she doesn't know what states are accessible to it. She has no information about what. I have another photon here. Boom. So she decides to measure her system. But remember that her system is entangled with Bob's particle, right?
Okay.
Right? So this puts Bob's particle into a state that is in the set of possible states of the measurement. So when you measure something, and it basically collapses Bob's photon into a state, right? When she measures it, because they're entangled.
Yeah.
So this entangles it, But the thing is, Bob knows how to transform this collapsed state, back into the original one.
Okay.
through a series of transformations. Now, we know how to do this in physics.
I'm going to be honest, I'm getting extremely lost.
Okay. Well, in the abstraction, like we know how to do this with the math. Like you can do a series of transformations.
Okay.
And get back to the original state, right?
Uh-huh.
So the idea is that you can essentially, Bob can recreate the original system and now have information of the same particle Hamiltonian that was given to Alice.
Okay.
Or that Alice had. To kind of make sense of this, I'll put this little video up. Because this was a little bit mind-blowing, because I was like, how does this, the hell is quantum teleportation? You know, how does this, what the hell does that even mean?
Right.
And maybe this will help elucidate a little more.
Well, classical teleportation is very easy. I can make a model of an object, I can measure all the dimensions of it, I can measure the positions of all its components, and I can send that digitally from A to B, and then using, say, some sort of rapid prototyping machine, I can construct a copy of that object. When it comes down to quantum states, there are physical rules which say you cannot copy them. Effectively, if I take a superposition state of a 1 and a 0, I cannot clone that. I cannot make an exact copy. I have to choose a measurement basis in which to measure it and project it into 1 or 0 state. So I can't get these alpha and beta coefficients. However, we can use this technique of quantum teleportation, where effectively we make a joint measurement of this quantum particle with another quantum particle that is entangled with a remote quantum particle over here. By measuring what is effectively the difference between this particle and this particle, we get an answer which actually is only 1, 2, 3, or 4. In other words, one of 4 possible answers. And we can take those 4 possible answers and perform 4 possible manipulations on this remote entangled photon to return it to this alpha plus beta superposition state. And that is what teleportation is.
I mean,
so did you see what kind of fucking how confusing that guy was?
Yeah, it's pretty confusing. Quantum mechanics is so confusing. Because then the thing is, people don't explain what the coefficients of things are. I can explain what the coefficients of things are because I know it, but I can't synthesize all of that because I don't really understand. But the thing is,
let's break this guy's example down, like what he's trying to say.
So one of the things is they want to capture. I guess one of the main aspects they want to capture is the alpha or the beta. And the alpha and the beta represent the coefficients for those quantum states. And the quantum states are those vectors in Hilbert space, right? These are all like these abstract terms and whatnot, but who cares, right? Yeah. Ultimately, alpha and beta represent probability distributions. So the 0 would be the 0 state of the qubit, and the 1 would be the 1 state of the qubit. Alpha is... and the thing is, of course, in quantum mechanics, as I'm sure you've heard, they can be in 0 and 1 at the same time. So you can range alpha and beta along this axis of, -1 to 1, right? And then you can even make them complex numbers like I. Yeah. So it can be 0.8 I if you want it to be. So when you square those coefficients, you get a probability. So you get a probability associated with 0 and a probability associated with 1. So that means that you can see when you measure that state over many iterations, right? You'll eventually get out that specific probability for that state. So let's say if your probability was 0.8 for alpha or 0.8 for 0, I'll replace, I'll say 0.8 for alpha, which is on the 0 state. I don't remember if that's what he has. Okay, the alpha's on the 1 state. So let's do 0.8 is the number for, or square root of 0.8 is the number for the 1 state. When you square that, you'll get 0.8, which is 80% of the time you'll get a 1. So I guess that's what you want to get. That's the information that's valuable in a quantum system. Beyond that, I don't really want to say much more because I'm not as clear on that. But I guess the utility in that is the fact that you can say, like, if you're trying to understand, if you're trying to understand the probability of some specific system in quantum mechanics, the the information you'll get back is basically that this is going to be a one state 80% of the time, and this is going to be a zero state 20% of the time. So yeah, much more than that, I can't really give much. I was kind of lost in his video. I didn't really.
Yeah, I don't think he did a great job. Like he does. This is the thing. Like he does introduce the setup pretty well. And I don't know why they arbitrarily chose us to do this in 2 minutes.
Yeah.
This guy should have spent a little bit more time explaining this. Because the way that Schrodinger kind of portrays it, it seems like maybe Schrodinger's example is a little too much of a toy.
Okay.
But in this.
Oh, was this the same example that we were talking about just earlier?
Yeah, but a little bit.
Oh, wow. I didn't even get that at all.
He seems to modify this a little bit.
Okay.
Because like here, I guess like Alice and Bob are sharing again the entangled pair. Yeah. I guess so photons here.
I think MichaelNielsen's video is way better. Just saying.
Yeah, and so this teleportation aspect is essentially you're not necessarily cloning anything because the no cloning clause says that they have to have a shared. I just don't understand what's cloning mean in this context. I think like literally, okay, like in classical stuff, like we make copies. Like we do clone things like quite 1-to-1 essentially.
Do we though?
You don't think so?
No, I mean, in what sense? For what? Nothing I can think of.
Like if you write the bits, well, I guess the bits aren't 1-to-1 because it's a recreation of the information. But I mean, I think that seems. I don't know if this is something that's very technical just yet. It might have more deeper implications because, as far as I know, the no cloning clause, the no cloning clause apparently has to do with you can't. It's this impossibility of perfectly broadcasting the information contained in an unknown physical state, and that's kind of what they mean by no cloning. Which, I mean, at face value makes sense, but in this particular example of the quantum teleportation, the guy doesn't really illustrate that well enough. But like the toy model that Schrodinger gives, I feel like is kind of illuminating because you can sort of Bob in the example that I was saying was able to sort of access by a series of transformations. Ideally unitary, you know what I mean? Like you can kind of like go back and forth. You know,
sure.
Like in quantum mechanics, like unitary transformations preserve the whatchamacallit. I'll add it here. I'm just gonna dub this with the actual thing. But unitary transformations have a lot to do with this because they show what kind of transformations are allowed and which ones aren't, and you can get back to the original state. You know what I mean? There's certain measurements that are unitary, right? Like you can perform and get back to your original quantum state, right?
Sure.
Like okay, yeah. I'm just trying to make sure we're on the same page. But like there are certain qualifications for certain types of measurement that are said to be unitary, and that's to do with like the mathematical like Hermitian conjugate stuff, all that. And but anyway, let's not get too much bogged down in the fucking theory because
the quantum theory is talking about quantum mechanics is always a trap.
It is because you got to think about the math.
You really got to study a lot to synthesize this information.
Yeah, and you got to see the math.
And unfortunately, I did not study enough for this one, so I hope at least someone will understand at least an iota of something from this.
No, I think they will. I hope that this quantum transportation video has been illuminating enough. If not, I'm going to go ahead and include this other one, but it's a little bit more lengthy. But anyway. But what's interesting also is the concept of like this idea of like entropy comes in. Because entropy, as Shannon showed, and this is the physicist, I believe. No, he wasn't a physicist. He was actually just did information theory.
Yeah, like a computer guy or something.
Yeah. he showed that information is kind of this more fundamental thing.
And damn, was he right. I feel like information theory is like the leading edge of physics in many ways.
Yeah.
That's like the untapped nectar that's available to us right now. Like, I feel like some major discoveries are going to start coming about from people really understanding the relationship between information and quantum mechanics.
Yeah. Or physical quantities. Like, if you remove the physical quantities from, like, maybe we're too materialistic, and we've had conversations about this, but as physicists, maybe we're too tied to the materialistic aspects of particles and whatnot.
Yeah.
And maybe
we're very tied to, and we keep, man, this is so annoying with quantum mechanics, is people keep ascribing classical intuition to quantum mechanics.
Yeah.
When you say things like a particle can be in the state of 0 and 1 at the same time, yeah, you're technically right in some sense when you're thinking of it mathematically and trying to, but you're like invoking this classical intuition on the system that really messes up someone's understanding of the system.
Yeah.
Quantum mechanics is just in a superposition of states. That's really the baseline of what you can say.
Yeah.
It's actually more distracting to try to put that classical intuition on top of it because, you know, your brain doesn't understand what that means because it really isn't, like, the quantum system at the end of the day is not doing that. It's like you're like thinking backwards in some sense.
Yeah.
It's like this is the superposition is the fundamental layer.
Yeah.
Classical mechanics builds up from that. So you saying that it's in a 0 and 1 at the same time is misleading, very misleading.
Yeah. No, very true. And like the fact is that von Neumann actually had a conversation with Shannon about this.
Yeah.
And he convinced Shannon that that this was that what he was trying to talk about was entropy. Like in physics, we don't have a real definite concept of what entropy is supposed to be, but Shannon kind of created this at the time. Not really. Like at the time, we had this kind of like loose concept of what entropy is supposed to be. Like blah blah blah. But he made the connection that information is entropy in some ways. Like it looks you get the same results in a lot of ways, and so it.
And the one that really kind of elucidates that is Maxwell's demon in some sense, I believe.
Right, yeah.
Because the whole thing with Maxwell's demon, which was a thought experiment in statistical mechanics where, you know, you can kind of separate or you can decrease entropy in this region. And people were scratching their heads at how this is possible. You know, they had these these two doors, and then you can send, you know, an intelligent demon could just let through the certain particles that were above a certain energy regime, and then actually decrease the energy in one section of the box.
Yeah.
And then they were actually saying that some of that entropy gets pushed into the demon itself because he knows something about the information of the state, and that's when you kind of have to recognize the information aspect, which is where Shannon's entropy comes in, I believe.
Yeah, entropy and meaning. Yeah.
Big asterisk on that because I didn't research that for this, so please fact check that completely if.
Well, no, I mean that example is actually really illuminating for like for what kind of Shannon entropy is, and like and you get meaning from certain things, and how that is a cost. There's a cost of information there.
Yeah, it's like you're not getting around. You're not decreasing entropy somehow.
There's information. There's like a cost to encoding the information.
Yeah,
and
something
decoding.
like that.
Yeah, there's a cost of information encoding and decoding. But like for instance, I'll give something that's kind of illuminating and hints at something a little bit deeper in the physics. This has to do with Shannon entropy and meaning, and I'll go ahead and play here just the beginning of it here.
Sure.
Quantitative measures to quantify the
Wait a minute. Once more, we forget to press the play button.
channel capacity needed to send messages through electronic telephone lines. And it is often said that Shannon's entropy does not quantify meaning, which is to some degree correct in the context of communication theory, because Shannon entropy seems not to care about the meaning of a message or its actual content. In other words, Shannon entropy does not care whether you are trying to send a message such as "I'll meet you for lunch on Tuesday, 2 p.m., or a possibly random looking number such as 84592646. However, there is another angle to Shannon entropy that suggests exactly the contrary, and it is both what makes this measure interesting but also its limitation. Meaning in Shannon entropy is deeply encoded in the form of the underlying assumption. In other words, the context in which a question related to entropy is made. For example, if the number 8459246 in our example is a telephone number, it makes a lot of difference because the underlying ensemble for the entropy measure is over the distribution of not all possible numbers, but only the set of valid telephone numbers. So Shannon entropy cannot only distinguish between data if we start from knowing that a sentence is written in English or is a telephone number. So this information makes entropy to care about meaning, but at the same time provides no tools to update the underlying assumptions or seek for that knowledge. We will see later how this is different with algorithmic complexity. Otherwise said, if you have any knowledge of the ensemble for your distribution, then Shannon entropy is all about meaning. For example, the sentence "I'll meet you for lunch on Tuesday 2 p.m. only has meaning if you know that this sentence is written in English. So by knowing that this sentence belongs to a subset of well-formed English sentences, then the entropy of the sentence becomes significantly lower than assuming that the string can be in the space of all possible letters and words, for which the entropy would be much larger. The problem with entropy, so to speak, is not that it is unable to convey or capture meaning, but that it is ambiguous and fragile for exactly the same reason related to probability distributions. Because Shannon entropy by itself does not provide any means to estimate the probability distribution, and so it relies in practice on traditional statistics or the observer's beliefs or lack of knowledge. In general, one ends up using a general assumption for the uniform distribution, which makes entropy to become a trivial function of symbol counting. Indeed, if the uniform distribution is assumed, as it is in most cases, what Shannon entropy is measuring is the multiplicity of the different symbols used in a sequence, just as it does its counterpart measure of entropy in physics that counts the number of possible microstates, such as particles or molecules in a given volume of space. Leaving those arguments related to meaning and the limitations of entropy aside, there are interesting properties of entropy worth mentioning and studying. For example, one of the general properties of Shannon entropy is that redundancy does not add new information as one would theoretically expect. Once fixed the number of symbols or letters, the greater redundancy, the lower the entropy. For example, repeating the letter E at the end of some words does not provide any new information than the original sentence and as a function of the sequence length. So the entropy drops just as it can be seen.
I thought this was fascinating.
Yeah, I don't really even know what that means.
like redundancy doesn't increase entropy.
He said it drops though.
Yeah. Like
How
it
does
ends
that
up.
make any sense?
I guess because there's more order when there's more redundancy, or it looks like there's more order when there's more redundancy.
I feel like this is too
This is
is
very
too deep for me to riff on.
No, but
if we're gonna go here, I'd have to study
it's
way
very
more.
fascinating, right? Like this is just like wow, okay, like this sort of the Shannon entropy. I mean, he's right. Like Shannon entropy doesn't say anything about sort of ascribing meaning to any of it, right? It's just like you're just kind of given an ensemble. In the physical example, it's like you're given an ensemble of particles. They don't have meaning until they have arrangement, and like, you know what I mean?
Right.
Like, this is kind of one of those paradoxes about living organisms, right? That's like a huge like how do living beings even
Like, how are they animate and like?
Yeah, how do they exist? How does life even come to be? If it seems to violate our known laws of entropy, I guess, right? Like the sort of
we can decrease entropy locally.
Well, that's the
if that's
thing.
your
Yeah. But that's kind of the thing. We had to kind of fine tune our understanding a little bit more to see that we actually increase our entropy locally.
No, we decrease.
No, sorry. Yeah, but globally. Sorry.
Yeah.
I meant the inverse. I'm sorry.
Yeah, like humans love to decrease our entropy locally.
Yeah.
Which you almost like, how's that even possible?
Yeah.
Because I think everything else in the universe is not animate increases entropy.
Yeah.
I believe. Please put a big giant asterisk on that because I haven't thought of all the scenarios. Entropy's so deep. We should do a whole podcast on that. We really should.
Oh, we actually, that surprises me. I don't think we have.
I don't think we have either. I think it's because one of these things. It's like in the realm of like principle of least action, entropy.
Yeah.
It's like one of these things where I've been avoiding it for so long because it's so deep, and it's like probably one of the hardest. It's in the regime of one of the harder concepts for me to be able to really understand.
Yeah, it bleeds. But this bleeds into this Shannon entropy, or this idea of like how information is given meaning in certain contexts and whatnot, and there's a lot more there. How meaning is contextualized and all this other stuff. It gets into the quantum realm, and I guess you could say the von Neumann one is a little bit more fundamental because it fundamentally is a quantum mechanical one. And I'll go ahead and show a video here that good old PBS Spacetime did a couple weeks ago now. So they have the big budgets for the infographics. So
yeah.
They're like.
I think somebody said the guy's name was Matt, by the way.
Matt?
Yeah, I think we called him Mark or something in the last
shout
episode.
out to Matt. He's great. Him and his team are great.
Yeah, he's killing the game.
Yeah, but fundamentally, the von Neumann relation, or von Neumann entropy, is really, if entropy is for information, that's really the source of how we manage quantum information. And I'll go ahead and put an equation up here of what the von Neumann entropy is. It's the limit as n approaches infinity of like the number of states, or the entropy is equal to the number of states and the quantum system over the number of trials. So sort of like on the top, it's the number of qubits in your system, blah, blah, blah. And
isn't it the logarithm?
Yeah, I think there's a logarithm involved, but this is coupled in another term. But I'll go ahead and show the simple like image of it.
Sure.
In case you want to look at the physics of it.
It'll be right.
It'll be right in the middle here. But this is basically the root of quantum information. This is where it all begins. And this is where von Neumann, that kind of credited to be the sort of founding father of this in some sense.
Right.
Seeing this connection. So to elucidate on this a little bit more, we're going to go to the PBS Spacetime video they did on quantum entanglement and how you get entropy from this.
Okay. So then why was it called entropy and not like von Neumann-tropy or something?
I don't know. I think von Neumann told Shannon, don't call it Shannon information, call it Shannon entropy. He was the one who kind of told him directly to do that. So it's like kind of weird that
entropy is a cool ass name.
It is. I don't even know.
That's one of those things like, we were talking about the unlockable characters back in with the QFT.
Yeah.
Like these big physics concepts, you're like, I got to get to that. Yeah. That was one of those for me for sure. And I still am like, oh, I see why I never learned about this because it's just too complicated for me.
It's very deep. It's not. I don't think it's given a fair treatment.
We really need to do a podcast on. I need to just man up and just really research the hell out of entropy because this is like so overdue.
Yeah, and I mean, like, look, this doesn't even touch on all the. I haven't even gotten to the actual. Like.
Yeah, entropy is so deep.
Yeah. No, I'm just saying, like, even all the stuff with like. How would you say, like. All the stuff with the modern quantum computational stuff.
Right.
Like, there's just so much to say about quantum information and how we're kind of like learning about it. In 1973, like there's I think it was a physicist or a computer scientist, Bennett, last name Bennett, was kind of demonstrated that you can make a universal Turing machine reversible for any computation, which is a required step in the design of a quantum computer, because you want to have unitary operations, you want to have reversible operations and stuff, or unitary state transformations, so you can go back and forth between, the states. Anyway, and there was another scientist, Benioff, not to be confused with the Game of Thrones writers.
I'm not aware.
Benioff, yeah, he who shall not be named. anymore because they destroyed a brand, a beautiful brand.
But you got to give them credit for 5 good seasons or something.
Yeah, at least 5.
Yeah.
At least in my opinion, 5.
That's pretty damn good.
Yeah, we'll never talk about the other seasons after that. But Benioff developed Hamiltonian models for computer systems or classical computer systems. But it was actually David Deutsch. Sounds familiar?
Yeah, it does. I don't know who that is.
David Deutsch is actually kind of the founding father. This was 1985, 1989. They characterized the essential features of a universal quantum computer and formulated the first genuinely quantum algorithm. Yeah, David Deutsch.
Gotcha.
So that's why his name sounds familiar.
Yeah.
Because me too. I was like, what? David Deutsch?
Yeah, it's like a name you hear in passing, but then you never hear it again.
Yeah.
Yeah.
So you can thank David Deutsch for essentially sort of making quantum computers even relevant to begin with.
Putting it on the map.
Beyond the proof of concept.
Right.
Yeah, it's so Deutsch laid down the foundations of like quantum logic gates and quantum networks and all that. You have like different quantum algorithms that come from that for performing like computational tasks.
Yep.
More efficiently, obviously, than classical algorithms.
In some cases.
Yeah, but most famously being Shor's algorithm.
Yes.
And this is like somebody asked us to do an episode on Shor's algorithm.
Well, someone actually asked us to do an episode on Grover's algorithm.
Oh, okay.
But I figured, if we would do an episode on Grover's, when we might as well do one on Shor's, right? It's like obviously.
But yeah, maybe we can do that one day.
So for the audience, like the thing is Shor's algorithm, like that's another term that I kind of gets thrown around. Like I'm like, it deals fundamentally with like prime factorization, right? Mm-hmm. Like that's like I don't know, do you remember much about this?
Yeah, so Shor's algorithm is basically, like you said, it's prime factorization. So one of the schemes that we use for RSA encryption and just, I guess, some of the major cryptographic schemes that we have for, like, banking information and, like, HTTPS, things like that, they can use primes, really large primes, as a way to what would you call it? As a way to secure information of some type. Mm-hmm. And it's like you have to know the prime factors of that really large number to be able to crack those keys. Mm-hmm. And Shor's algorithm should be able to crack those keys in a reasonable amount of time, whereas right now it's like some kind of crazy exponential time that's, in the order of the age of the universe if you did a kind of
classical
brute force kind of method using classical computers. But with quantum computers, you should be able to crack it, in significantly less time, apparently.
Yeah, and it's the simple prime factors of a positive integer, like n equals p and q, like two different numbers there. Yeah, and I mean, Shor's algorithm is like huge because it could essentially break our whole like sort of information security infrastructure, right?
Right. Like you can hack into like government databases because you can just brute force the password with the quantum computers. Yeah.
Banking.
But I think they've said that there's some regimes of quantum mechanics. I don't really know this for sure because I haven't researched it, but there's some new leading edge stuff like that have more security against Shor's algorithm. Like I know there's like elliptic curve fitting, which is another method that's used to encode or protect information. And then there's, even larger schemes for RSA that maybe would overwhelm a quantum computer. I'm not really sure. But there are methods, I believe, that are devised to be quantum proof, potentially. Yeah. I'm not sure, though, so you're going to have to look that up. But they're definitely working on it for sure.
Yeah. Just insane stuff.
Yeah.
Just like this, and this is kind of the thing. This is, like I was saying, a modern working field. Mm-hmm. So they're constantly developing new concepts by studying the foundations of quantum mechanics.
Right.
Like you're studying entanglement more. Like, we're pushing the limits on how you can get things to superposition, the number of particles you can get in superposition. Like we're testing limits right now of our
which is why it's so hard to say what the applications are going to be potentially, because it's like it just keeps going, right?
Yeah.
When you crack major areas of fields like this, then just like you get a waterfall of applications that you haven't seen before.
Yeah, so this is why it makes this is a field that I think a lot of people don't talk about.
What?
Quantum information. Like, I've never seen
I
it.
wouldn't say that.
I don't think it's advertised.
There's tons of YouTube videos on quantum computers.
They are, but think about, we went through the whole rigmarole. Like, at no point did anybody ever say anything about, like...
Oh, in school?
Yeah.
Yeah,
Like,
no.
Even,
no.
like, just now, as I was leaving grad school, they're going to offer a quantum information class.
Right.
And
Yeah, everything I learned about quantum information was on my own.
Yeah.
Like the whole delayed choice quantum eraser, we never even mentioned that. And I'm like, that's such a, like, to me, such an important experiment that I can't believe I've never heard of until, like, literally, like, a few weeks ago.
Yeah. But that's the thing. These are foundational. I think these are important foundational aspects of quantum mechanics that we obviously need more, how would you say, attention, maybe? Yeah. The shut up and calculate method has kind of failed in giving... Well, it's not failed entirely.
Not failed for sure.
But it's
very
giving it has some it has a lot of utility, but there is the aspect of, like, let's sit down and contemplate.
Yeah, yeah.
The whole I think you said that.
Right, that's my answer. That's my response to shut up and calculate. Slow down and contemplate.
Yeah. Because we do need to sit down and think about these things a little bit more. But shout out to PBS Spacetime. They actually do a great job of making great content that is that kind of, like, pushes the envelope on this stuff a little bit, right? Mm-hmm. On the sit down and contemplate thing.
Right.
But anyway, so let's go ahead and play this. This has a lot to unpack. So.
And there is indeed a type of entropy that applies to quantum systems, like our air molecule. It's von Neumann entropy. And understanding it may help us understand not just the second law, but also the arrow of time, and how the large-scale world emerges from the quantum world in the first place. Now, before we dive into that, let's review our more familiar definitions of entropy. Ludwig Boltzmann recast entropy in terms of the number of configurations of particles that give the same set of crude thermodynamic properties. For example, there are more configurations of particles in which energy is perfectly mixed than if energy is concentrated in one spot, like in our piston chamber. Systems will tend towards the more common configurations, hence entropy increases. Here we start to see the connection between entropy and information. If all the air is in the corner of the room, for example, then you know more about the positions of the individual particles. They're all in the corner of the room, versus if they're spread through the room. But it took the invention of information theory to really see the connection between information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon Entropy. Shannon Entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more. Another way to think about Shannon entropy is in terms of events. The more possible outcomes of an event, the more entropy the event has. For example, a flipped coin is a low Shannon entropy event because it only has 2 outcomes, while flipping 1,000,000 coins is a high entropy event. Shannon entropy is actually more fundamental than thermodynamic entropy in that it is a generalization of the more familiar entropy. It applies to...
Let's unpack that. Does that make sense?
Yeah, I think so, because the Shannon entropy has to do with information theory. And we keep coming to the answer that information is somehow more fundamental to, like, quantum mechanics.
Yeah.
So that makes perfect sense to me. I mean, it definitely does.
Mm-hmm. Yeah, I like their illustration there. That's kind of like a good way to think about the complexities, I guess, that go into it.
Mm-hmm. Any system of information and any type of action that reveals that information. When he first came up with this theory, though, Shannon didn't fully realize its importance. As the perhaps apocryphal origin story goes, he only started calling his invention entropy after talking to the great Hungarian mathematician and physicist John von Neumann. Supposedly, von Neumann said that he should call it entropy for 2 reasons. 1, it looks exactly like the equation for thermodynamic entropy, and 2, Nobody knows what entropy is, so nobody would argue with him. But von Neumann probably knew perfectly well that Shannon's entropy was the real deal. One, because von Neumann was a savant-level genius who had out-mathed and out-physicsed many of the greatest minds of the last century. And two, because of part one, von Neumann had already invented his own brand of entropy, von Neumann entropy. It's the entropy of quantum systems. And because everything else is made of quantum systems, it may be the most fundamental definition of entropy. Even Shannon entropy is just a special case of von Neumann entropy. At least, so says von Neumann himself. The concept of von Neumann entropy is at least incredibly...
Yeah.
That's interesting. So he's saying the quantum version of entropy is more fundamental.
Yeah, if you think about it, right? If it's like... Because, like, I mean, if statistical mechanics kind of orders the way... You know, how particles of ensembles come together.
Yeah.
In some way, the von Neumann example of quantum mechanics kind of tells us about how everything else emerges.
Okay, so maybe I misunderstood what the definition of Shannon entropy was, because I was thinking that his was more fundamental than the von Neumann entropy.
How so?
Because I was thinking the von Neumann one was quantum, which it is.
It is.
But then I was thinking that lower than quantum would be information theory somehow. But it seems more like statistical.
Well, Shannon.
Statistical.
No, the thing is, they are. Well, the funny thing is that they're almost completely analogous.
Yeah.
You know what I mean? Like they don't look any different, really.
Right, but I think the fundamental comes within the qualitative interpretation of them.
Right. Yeah. Exactly.
So, but yeah, entropy. I can't really speak with confidence on entropy.
So we'll
let Matt take it away.
Powerful. It's at the heart of quantum information theory, enabling us to calculate how much quantum information is contained in a system, and it can also be used to determine how many bits of classical information we can get out of the system when we make a measurement. But perhaps the most interesting, von Neumann entropy tells us the amount of entanglement in a system. In fact, it's driven by entanglement, this mysterious connection between quantum particles that Einstein called spooky action at a distance. As a bit of a spoiler, von Neumann entropy seems to reveal that the evolution of entanglement connections is what drives the second law of thermodynamics. Okay, we're getting ahead of ourselves. To get a glimmer of understanding of what von Neumann entropy is about, let's think about information in quantum mechanics. Here is a counterintuitive thing about superposition. After you flip the quantum coin, you actually do know its current unrevealed state. That's because its state is entirely defined by its superposition wave function. It is in a pure state of 50% heads and 50% tails. This is subtly different to the state of a classical coin, which is either heads or tails with a 50% chance of each. That superposition really represents the coin's current reality from your perspective. But if you have full knowledge of the unrevealed coin's current state, then there is no hidden information, which means its entropy, in this case its von Neumann entropy, is zero. Observing the coin doesn't reveal new information about that unrevealed state, rather it changes the quantum state in a random way, now 100% heads or 100% tails, but the information about which way it would go wasn't hidden in the unrevealed wave function. This is very different from the result of flipping a regular coin, which is entirely heads or tails before you reveal it. That information is embedded in its wave function, it just isn't known to you. So the regular coin's entropy, in this case its Shannon entropy, is positive. In case superposition wasn't weird enough, let's bring in quantum entanglement. That means we need a second coin. It's spookily connected to the first, in that when both coins are flipped, they have to land opposite to each other. After the flip, we say that the flip results are entangled. They are correlated. Even though we don't know the individual results, if we reveal one, we'll immediately know the result of the other. So, you flip your pair of entangled quantum coins. There are two ways that they can turn out. Either the first coin lands tails and the second heads, or vice versa. Before they're revealed, they exist in a superposition of states. Both possibilities exist simultaneously. The unrevealed wave function is like this, which means 50% heads tails and 50% tails heads. The von Neumann entropy of that entire wave function is still zero because the combined wave function of the two coins holds all the information about their current state. But what if we consider only a single coin? Because of the entanglement, the the part of the wave function corresponding to a single coin does not contain all the information about the coin state. Its von Neumann entropy is no longer zero. Information is hidden. It's hidden in the part of the wave function corresponding to its entangled partner. And this is where we can connect von Neumann entropy to all of the other forms of entropy and glimpse the real origin of the second law. When viewed with its entangled partner, the coin exhibits quantum weirdness like superposition, and that could be revealed in experiments like a Bell test, which we covered previously. But treated individually, each separate entangled quantum coin behaves kind of like a regular classical coin. For example, it doesn't by itself exist in a pure superposition of states. That superposition only appears when you include its entangled partner. It's in what?
Yeah, there's a... I think this kind of has to do a little bit with like the sort of, when you think about hidden variables, Einstein had this idea that like like the idea of even saying hidden variables, that means that there's hidden information, right?
Sure. Yeah.
Right?
Yeah.
Like, because, I mean, really at the crux of it, you are trying to measure something. You're saying there's some other thing that we're missing. There's some other information that we're not getting.
Right.
But the von Neumann entropy formula, I guess, looking at it in this kind of like foundational aspect, it's saying, again, I guess pointing to that being a feature of quantum mechanics as opposed to like a thing that's
an incomplete part of the theory.
Yeah, this is the problem with intuition, where Einstein got misled because his intuition was so good in the classical regime, and then slightly extended with the relativity. Although I feel like relativity is a little bit more graspable with intuition, because you can almost visualize these things once you get it tuned up.
Right, because you're thinking about how fast things are moving, and it's
and then you're like, okay, I can think of contraction, I can think of time dilation in some kind of sense, right? And then you can just shift to relativistic frameworks. It's still tough, but you can almost visualize it.
I mean, he had a basis for it.
Yeah,
the Galilean stuff,
right?
Galilean transformations.
But then quantum mechanics is like, you can't even really visualize that. Like, how the hell do you see superpositions? How the hell do you see entanglement? Like, it's tough. Like, I don't know if you can even visualize that. You can't visualize a Hilbert space, right? So it makes sense. Like, Einstein he's an intuition guy, and he's relied on it so heavily because that was his strength. When you're trying to go to quantum mechanics, it breaks that whole way of thinking.
Yeah.
So I understand completely why Einstein would have those objections, because quantum mechanics is basically a shut up and calculate regime of physics.
Right.
You need the math, or else you're not going to understand.
Yeah, and I mean, I don't blame him, but it feels like kind of like when people are saying like, there's no hidden variables, there's no hidden information, kind of like they're taking shots at Einstein a little
right. But Einstein's objections were actually some of the most critical pieces to shedding light on how weird quantum mechanics really is, and then really strengthening it to show that this is really what the fundamentals of reality are.
Yeah. I kind of wanted to go to this like view of pure and mixed states, because that's something that does come up weirdly enough. I'm going to say the timestamp here is 1045, but it says pure versus mixed quantum states. A pure quantum state is a state which can be described by a single wave function. A mixed quantum state is a statistical ensemble of pure states.
Okay. So I guess it's just a linear combination of wave functions or something? Or I don't know.
Yeah, I guess like the pure quantum states are the ones that you see typically in the sort of coin examples, right? That's a pure quantum state. It's like 0 or 1, kind of binaries almost.
But then again, I think multiple particles are still described by a single wave function.
Well, that's the mixed quantum state, because now you have an ensemble.
But
like
I think they're still all one wave function in some sense.
Yeah, they can be.
I think they have to be.
No, they're represented, I guess, because you can apply them as linear combinations, right? Like you're saying. So yeah,
maybe let's put a big asterisk on that.
I think a mixed quantum state is the combination of pure states.
Okay.
You
could
say
it.
What it is.
I'll say maybe.
Okay, cool.
What we call a mixed state, heads or tails, not heads and tails. And just like the regular classical coin, it has non-zero entropy. This similarity between the classical coin and the entangled but isolated quantum coin is no coincidence. Its entanglement is the first step in the transition between the quantum and the classical world. Our capacity to observe quantum effects like superposition depends on being able to access the entire wave function. With one partner coin in entanglement, that becomes more difficult. But as a quantum object interacts with the countless particles of a macroscopic environment, and those particles interact with each other, the web of entanglement grows so quickly that it soon becomes impossible to access the entire wave function. We call this process decoherence. It's how the ordinary macroscopic world emerges from its very weird quantum pieces. Looking at it this way, our classical coin is just like our isolated entangled coin, except now we don't have a simple entanglement between two coins. The entanglement is between the coin's countless constituent quantum parts and every particle they've ever interacted with. That network of entanglement is in the superposition of states, heads and tails, but you can't ever access it, in part because you're part of that network. You've already become entangled with the coin and live in the slice of the wave function, the mixed state, where the coin is either heads or tails. The propagation of entanglement leads to our experience of the very unquantum macroscopic world, but it also drives the growth of entropy. Information about the detailed quantum states of all the particles becomes increasingly inaccessible, leaving only crude observable properties. For example, thermodynamic properties like temperature. We call these properties that are preserved through this diffusion of entanglement pointer states, in the language of quantum Darwinism. Over time, systems move towards a state of maximum entanglement, at which point most information is hidden and the systems are describable by the fewest properties. For example, when a system equalizes to a single temperature. So there you have it. Growth of entanglement drives both the second law of thermodynamics and the emergence of the classical world from the quantum. And as an extra trick, it also defines the arrow of time, which itself points in the direction of increasing entropy and multiplying entanglement, as of course we've discussed. But there's a lot more to talk about because von Neumann's insights lead us to a picture of reality that is more informational than physical.
Mind blown.
Care to explain? I was zoning a little bit.
Matt, mind freak with Matt from PBS Space.
Mind freak. Now that's a throwback.
Yeah. Truly, PBS Space Time should just have Matt be the mind freak. Just have him as like a, what's his name?
Chris Angel.
Yeah. he's the Chris Angel of physics.
Right.
About to blow your minds, people. No, the revelation of this sort of how quantum entanglement, that's kind of the foundation of all this, the information theoretic kind of point of view, and how it gives rise to the classical kind of world. The decoherence is something that I think that you see a lot in quantum computing, because we kind of become more familiar with like a quantum state kind of coming out of the quantum state. It's said to start becoming entangled with its environment in some way. And so you can think about these phase factors in the quantum system. They pretty much start, I guess, phasing out in some way.
Okay.
So in this decoherence picture, what Matt was saying was that you couple, or the quantum system couples with its environment and other constituents of the environment.
Mm-hmm.
And as this ensemble or this mixed states increases, or so, like it couples with the other quantum systems.
It's like a runaway effect.
Yeah.
Okay.
So you start creating bigger and bigger systems, which then start bleeding into, now that you have, how would you say, he puts it in a language of information, but if you go back and kind of dissect that, he's saying it bleeds into having higher entropy overall. And if we're thinking about information, then this means like there's sort of like, it's a continuum. Like you go from von Neumann entropy or von Neumann information to Shannon information.
Mm-hmm.
It's a sort of grayscale. It's not like a clear, maybe there's a certain threshold. Maybe there's a certain number of particles where the ensemble or the mixed state becomes, you start getting decoherence. You start going into a classical kind of state, and you start getting classical information.
Okay.
You know what I mean?
Yeah, I see.
Fascinating stuff.
Yeah, very interesting. I feel like I got a lot of reading to do. I didn't know we were going to be talking about entropy.
Dude, like, truthfully, so this is this is all the physics foundation stuff. I think after that, it's engineering, math, and maybe computer science. Would you say?
Sure. Yeah.
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 But the technical aspects are still fascinating. Like, we still have, I think you were talking about a certain YouTuber that was going to go through a list of.
Well, it was just what we were talking about earlier with Superdense coding protocol. I had a video with MichaelNielsen, who has just an example of the Alice and Bob experiment.
I think is a lot better than the one that you show with the scarf guy.
Okay, cool.
Whatever his name may be.
I'll put that one in here just so y'all can see that in parallel, or I just make sure that that's included in the video.
Yeah.
But yeah, no, about the supercomputers, about the quantum computers. Sorry.
Oh, what about them?
No, just the different types, I guess.
Oh, I want to save that for another video.
Gotcha.
Because this was kind of the theoretical side.
Yeah.
Albeit I don't really know how tangible it's going to be, which I suspected, which is why I've been avoiding it for so long. It's quantum information is just a hard thing to tackle. I feel like I need multiple days of study for this one, but needless to say, I think I would like to do a video more on the experimental side of like what kind of quantum computers are out there, and and the hardware involved, maybe even the software involved as well, because it's just most people don't really talk about that. You always hear these videos talking about the qubit itself and explaining the theoretical side of things, but nobody really. A lot of people don't talk about the experimental side that much.
Yeah. True.
Yeah.
So we'll definitely get to those, and maybe we'll talk a little bit more about some of the sort of bigger, how would you say, not bigger concepts, but bigger points in quantum information.
Yeah.
Talk about accessible information compression in quantum mechanics, although that's more mathematical stuff. Entanglement assisted communication, like how you can kind of dive into those things. The computation aspect, I think we definitely want to get into, because that's definitely the more applicable stuff. And then quantum foundations, and that's probably going to be the last video of the series, just reflecting on the foundations of quantum mechanics. Kind of diving into where
you're making a lot of plans right now.
I am, but it's definitely something I've been wanting to tackle for some time. But yeah,
weird.
hopefully you've gotten some kind of background. I mean, we went through von Neumann entropy, a little bit about information that we can cover in like about an hour, and the relevant history leading up to it. So
sure, yeah.
So hopefully we'll be able to get into more detail in some other episode in future. So
Yeah.
That's the table sliding.
Oh, okay.
Yeah.
I thought we were about to be invaded by aliens. Shout out.
Yeah, hopefully the audience
Won't hear I don't think they'll hear that.
No, hopefully not. But anyway, folks, thank you for listening.
Indeed.
Don't forget to like, share, comment, and subscribe if you haven't already, and do all our socials.
Check out Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then thank you guys, patrons, once again. We appreciate you so much. If you want to become a patron as well, just check out patreon.com/Eigenbros for a 30-minute audio podcast every week. And then you can also check out the Discord. We, chat it up a couple, every once in a while. And that's it, I think.
Yeah, that's it. And we'll talk to you next week.
All right, guys. See ya.
See ya.